Good morning to one and all. This is Rama Krishna from KL University, dealing heat transfer lessons. Today, we will deal with heat transfer through composite slabs, and also we will try to understand what is thermal contact resistance. This topic will fall under the category of one-dimensional steady-state heat conduction without internal heat generation. At the end of this session, you will be able to understand what is a composite slab, how to evaluate the resistances offered by each layer for conduction heat transfer, and how to apply electrical network analogy to a composite problem, and how to estimate heat transfer through a composite slab, what is thermal contact resistance, and on what factors thermal contact resistance depends, and its effect in practical situations. Look at this figure. This is called a composite wall. The best example is the wall of your house is a composite wall. Composite in the sense it is made up of different materials. For example, if you take the wall of your house, you will have first a cement layer, and then you will have bricks, and again outside you will have another cement layer. Maybe outside cement layer, the center you will have bricks, and inside the room, to suppress the acoustic problems, etc., you may have a wooden carcassing. So under such circumstances, the heat has to flow from outside into the room, first through the cement layer, then through the bricks, and then through the wooden layer. So such a thing where you have more than one material offering heat transfer together is known as a composite slab. Consider three different materials here. One is having thermal conductivity K1, the other one K2, and the third one K3. T1 is the temperature here, and the end is the temperature T4, surface temperatures. And the interface temperatures are, say, T2, T3. Initially, we don't know what is the value of T2 and T3. Given temperatures are T1 and T4 only. Since T1 is greater than T4, heat will start flowing through the wall from one face to the other face. While the heat is flowing, first the material 1 offers resistance for heat transfer. It overcomes that and enters into the second material. Again, the second material offers resistance for heat transfer. It overcomes the resistance and comes out of this and enters into the third material. Like that, if you carefully observe, three different materials having different thickness offer different resistances for heat flow through them. But according to law of conservation of energy, if the heat entering into the wall is Q, the heat leaving from the wall should be also Q when there is no internal heat generation. Hence, the heat flowing through the material 1 should be Q, the heat entering into the material 2 should be Q, the heat leaving from the material 2 should be Q, heat passing through the material 3 should be Q. So the same amount of heat passes through these composite layers. This problem can best be represented in the form of electrical resistances like this. While heat is flowing through this, these three materials offer resistance for heat transfer one after the other. They do not offer resistance simultaneously. First, material 1 will offer resistance, then material 2 will offer resistance, and at the end the material 3 will offer resistance. So these three resistances are acting one after the other in series. You can represent like this. Heat entering through these is Q, the heat leaving here is Q, the heat here is Q, the heat here is also Q, because it has to obey the law of conservation of energy. Now these materials, being solids, they offer resistance in terms of conduction. Therefore, this R1, R2, R3 are the conducting resistances of these three materials. Because it is a slab, the resistance R1, conduction resistance for a slab, is given by the thickness delta X1 by K1, thermal conductivity of the material, into A. A is the area normal to the direction of heat flow perpendicularly to this surface. So it is similar to L by Ka, which we have seen in the last session. So R1 is del X1 by K1A, R2 resistance offered by the second material is del X2 by K2A, R3 resistance offered by the third material is del X3 by K3A. I'm sorry, this is del X3 by K3A. Now because all these resistances are in series, the total resistance is R1 plus R2 plus R3. So now Q, we know T1 and we know T4. So you can write the equation Q equal to T1 minus T4 between these two terminals, T1 minus T4 divided by resistance. The resistance is R1 plus R2 plus R3. We know T1, we know T4. You have calculated R1, R2, R3. Therefore, you can determine the rate of heat transfer through a composite wall. I will ask you a simple question now. How to find T2, temperature at point 2? Very simple. The heat flow through the resistance 1 is Q. The heat flowing through resistance 2 is also Q. The heat flowing through the conduction resistance 3 is also Q. Coming out is also Q. So now let us write the expression for Q between these two nodes, T1 and T2. Now Q is equal to T1 minus T2 by R1. You have already calculated Q. You know T1 and you know R1. So you can determine T2. Now next question. Once you know T2 and Q, how to find T3? Same analogy. The heat flowing through the resistance 2 is Q. So now between these two nodes, write the expression for heat transfer by conduction. Q is equal to delta T, T2 minus T3, resistance offered R2. Similarly, if you want to write an expression for Q between T3 T4, can you imagine Q equal to T3 minus T4 by R3. You understood? Suppose I want to write the expression for Q between these two nodes, T1 and T3. Then the heat transfer equation Q is equal to T1 minus T3 by R1 plus R2, because between these two nodes the total distance is R1 plus R2. You can also write Q is equal to T2 minus T4 by R2 plus R3. See, you can play with this circuit to determine the unknown parameters in this. You have several options. Whichever way you feel, depending on the data given, you can try and determine the interface temperatures and heat transfer through the wall. So very important application, because most of the materials or most of the constructions, most of the practical things are not simply with one material. They consist of layers of materials. Hence, a composite problem is very important from practical point of view. Now let us see one example. Imagine, yes, material is given like this. You are asked to determine the heat transfer through the composite wall having 4 different materials, A, B, C, D. Thickness of A is 3 centimeters. Thickness of B and C is 8 centimeters. Thickness of D is 5 centimeters. The left hand face is at 400, right hand face is at 60 degrees centigrade. Let us take the face area 1 meter square, but particularly for B and C, the areas are given as 0.5 meter square, half of the height, imagine. Now the equivalent electrical circuit, let us draw for it. While heat is flowing through this material from 400 to 60, this composite slab, first it has to pass through material A. So this offers what kind of resistance? Conduction resistance, RA. Then once it leaves A, it simultaneously enters into B and C. Parallelly it goes through B and C. Therefore, These two resistances, RB and RC, offers resistance simultaneously for heat flow. Then after coming out from B and C, the heat as a whole again passes through the material D, which offers only one resistance. So if you carefully observe, RA and RB, RC are parallel in RD. The temperature before the resistance A is 400, that is at this point, and the temperature after the distance D is 60 degrees. Let the heat flowing through this is Q. So the heat comes out of the resistance A is also Q. Now this Q coming out from the A simultaneously passes through B and C, so it divides into two parts, QB and QC, where QB is the heat passed to the material B and QC is the heat passing to the material C. It comes out, combines, and again it will become Q. And that Q passes through the D and comes out at 60 degrees centigrade surface. So now the formula for Q is equal to delta T overall by R total. Delta T overall means 400 minus 60 by total resistance. So between 400, this node, and 60, this node, you have 4 resistances. And what is the total resistance? RA plus, this is parallel circuit, so 1 upon 1 by RB plus 1 by RC plus RD. Now how to calculate RA? For a slab, conduction resistance formula is L by Ka. Here L is del XA by Ka AA. Del XA, 3 into 10 power minus 2 is the thickness. Ka, thermal conductivity of the material A, 150, area 1 meter square. You will get RA. Similarly, RB, del XB, thickness of the B, 8 centimeters, KB, 30 watts per meter Kelvin, area of B, normal to the direction of heat flow for B is given as 0.5 meter square. So you will get RB. RC, del XC, again 8 centimeters, Kc, thermal conductivity 65, area of C 0.5 meter square. RD, del XD, that is thickness 5 centimeter, K of D 50 watts per meter Kelvin, area 1 meter square. By substituting RA, RB, RC, RD in this equation, you will get R total. Once you know R total, you can determine Q value, delta T overall by R total. So R total is this much and Q value is this much. Now, as a matter of exercise, you can take up. We have found the value of Q given the temperatures 460. Now, how to find T2? Think over. I want to determine this phase temperature, T2. How? That is considering the heat flow along only one resistance. Q is equal to T1 minus T2 by RA. That's all. You know T1, you know Q, you know RA, you can determine T2. Next, how to find T3? Think how to find T3. You can consider the node T1 and T3, or you can consider the nodes T3 and T4. Easy. Now heat flowing through this RD is Q. The temperature difference across this RD is T3 minus 60. Therefore, Q equal to T3 minus T4 by RD. The unknown is T3. You can determine T3. You understand? So you got now all the interface temperatures. You know 400. You know this phase temperature at between A, B, and C. You know the phase temperature between B, C, and D. Now another question of interest. How to determine the heat passing through the material B and the heat passing through the material C? It's very simple. The heat passing through the material B is QB. Material B is offering a resistance of RB, and across this resistance the temperature difference is T2 minus T3. So how to write QB? QB is equal to RB by T2 minus T3. Similarly, QC is equal to RC by T2 minus T3. I strongly advise the students to go through the suggested reading books and practice more number of problems. Next, another important problem. To reduce the heat loss from the room, instead of keeping a single glass, they have gone for double plane gas window. And each pane of thickness 4 mm, 0.8 meters high and 1.5 meters width, having thermal conductivity of the glass 0.7, is exposed to outside air at minus 10 degrees centigrade with a convective heat transfer coefficient of 20 watt per meter square Kelvin. Please correct it. This is not watt per meter Kelvin, watt per meter square Kelvin, as stated in the problem. On one side, and to room air at 20 degrees centigrade with a convective heat transfer coefficient of 10 watt per meter square Kelvin. If the two 4 mm thick glass windows are separated by a 10 mm wide gap, which is filled with stagnant air having thermal conductivity 0.026 watt per meter Kelvin, and other conditions remaining same, estimate the heat loss and interior surface temperatures. Please note down the corrections. This is not 3 mm, 4 mm, and these units of HI, H0 are watt per meter square Kelvin, not in watt per meter Kelvin. The data given in this problem is correct. The representation is slightly differed. Now if you carefully observe this problem, you have three different layers for heat flow from inside to outside. Outside temperature is minus 10 and inside room air is at 20. So heat flows from 20 degrees centigrade to 10 degrees centigrade side. While it is flowing, first it has to flow through glass and then through the air gap and again through the glass. The air is trapped between the glass plates, so there is no motion of air. Hence, convection is absent, radiation is negligible, and hence we have only conduction mode of heat transfer through this air. So, glass offers first resistance, and then the second resistance is offered by the air between the two glass plates, and again the third resistance is offered by the glass. But if you closely observe, the convective heat transfer coefficients inside the room and outside are given. So which indicates that in addition to the conduction resistances of these three materials, the surrounding medium also offers some amount of resistance for heat transfer. So first heat has to reach the surface by means of convection, and then it passes through the glass by means of conduction, through the stagnant air film again by means of conduction, again through this glass solid by means of conduction. It enters from the glass surface into the outside environment by means of convection. So altogether, if you consider this problem, you have 5 resistances. First resistance is convective resistance inside. The second resistance is glass resistance. The third resistance is the stagnant air conduction resistance. Fourth resistance is again glass resistance. The fifth resistance is convection outside resistance. So all these resistances are acting one after the other for the flow of heat. Hence the total resistance is nothing but sum of all the resistances. So you can calculate convective resistance 1 by HIAI. Inside convective transfer coefficient is given as 10 watt per meter square Kelvin. AI, inside surface area exposed to the medium, is 1.5 meters width and 0.8 meters high glass plate. So it is 1.5 into 0.8, which is 0.83. And again, the glass offers conduction resistance, which is given by L by Ka. That is, please correct this, it is 4 mm as given in the problem. 4 into 10 power minus 3 by thermal conductivity 0.78, and area of this glass is again say 1.5 into 0.8, and R air, assuming that air is stagnant, it cannot convect, it only conducts. So again it is a conduction resistance offered by the air, L by Ka. Thickness of air film is, gap is 10 mm, 10 into 10 power minus 3. Thermal conductivity of air is 0.026, and area 1.5 into 0.8 is 1.2. Same thing. And again glass, again outside air 1 by H naught A. If you add all these things, you will get R total. Now once you get the R total, the Q value is delta T overall by R total. 20 minus of minus 10 by total resistance 66.12 watts. Now the inside temperature can be found using same resistance analogy, 20 minus T1 by R convection. So the inside surface temperature of the plate, this one here, glass plate, 20 minus say T inside by what resistance is there between the surroundings and the surface? Convective resistance 1 by HIAI. So that is what is written here, 20 minus T1 by R convection. So T1 equal to 20 minus Q into R convection, you will get 14.5 degrees centigrade. So if you observe, the inside surface temperature is 14.5, is considerably high, therefore it will avoid formation of fog on the interior surface. Instead, if you go for only a single glass plate without air gap, probably the inside surface temperature may fall well below the dew point temperature of surrounding air, which will result in fog formation on the interior surface, and that will spoil the environment of the room also. So therefore, in cold countries, to avoid the fog formation on the interior surface, instead of having a single pane glass window, they prefer 2 pane glass windows with air gap in between them, which will avoid the formation of fog on the interior surface.